In fact, I told you few lectures back when I had discussed the notion of the limit, and we came and discussed the notion of the velocity of a particle moving say in a straight line. So, and we looked at x as a the distance travelled as a function of time, and how do we calculate the instantaneous velocity, which turned out to be same as the derivative of that function. Now, I told you that you would understand calculus far better if you know at the very outset that every continuous function need not have a derivative, and second of all you would, which we will show now, and you will also understand calculus much better if you know at the very outset that this notion of derivative or integrals are names given to special limits. I think I have already told you. So, this is what you are taught at high school, right. So, if you have a function f, so I am just writing from R to R, it could be from AB to R, does not matter. So, the derivative at any point x we see how, if I make the change in x, how much x has f has changed. So, basically I am calculating the slope of the graph, slope of the line joining the 2 points x f x and x plus h and f of x plus h. So, that is the, this is exactly the slope. So, this is my coordinate point x f x, and this is my coordinate point x plus h f of x plus h. So, this ratio that you see is nothing but the slope of this line. Now, if you have h becoming smaller, so this was my x plus h, this was x and this was x plus h, so this was h. So, if h becomes smaller and smaller, so this will come here. So, here then we will be talking about the slope of, so x plus h will come here. So, we will be talking about the slope of this line, and as h becomes smaller, x plus h becomes nearer and nearer to x, we will finally be talking about the slope of the tangent at the point x f x, and the slope of the tangent at the point x f x is called the derivative of the function f at x. So, this, if this limit exists, then f is called the derivative. So, this limit of course must exist. So, if I assume the function is differentiable, so this limit exists. Now, because we have studied the notion of the limit in terms of this epsilon and delta stuff, then what we can do is the following. We will write down the epsilon delta in the epsilon delta language. What is the meaning of this? It means the following: given epsilon greater than 0, no matter how small, there exists a delta greater than 0 such that whenever mod of h is strictly less than delta and strictly bigger than 0, h is not equal to 0 of course, that we can't take the punctured neighborhood around 0, we are taking a neighborhood around 0, but not including 0, just as the definition of the limit, such that by the definition of the limit, whenever this happens, we have that this, the slope of the chords approach the slope of the tangent, which we have denoted as we call as a derivative. This must be less than epsilon. This is the meaning. See, if I look at this, I can do some more simplifications. Simply means that sorry, by h, this is strictly less than epsilon. So, we just made some simple modifications here, just made this more compact. So, what does this mean? It simply means that which also means minus 0, if I can write. So, this simply means there is minus 0 means just if you want to remove this as this. So, this simply means that 0 is the limit of this function as h tends to 0. So, here once I fix the x, this becomes a function of h, and that is the limit when. So, whenever given any epsilon and mod h is this, that limit, this limit of this function is 0. So, simply it means that the limit, another way of talking about or even you can write h goes to 0, does not matter, whatever you want, but okay, let me. This is nothing but 0. So, this is 0. This is another way of looking at the derivative. So, derivative actually approximates when points are, when you want to calculate f, you know when h is very small, you know that this difference from here, what you get? What do you get? You get f of x plus h minus f x from this part. This is what I get, f of minus f dash x h is lying between epsilon mod h and minus epsilon mod h. So, once the h is known, how much is my move from x, then this is, then the difference between f of x plus h minus f x minus f dash x h. So, this, if I can write this as some sort of an approximation. So, this difference is approximated by this, but this approximation has an error, and this error is bounded by the two numbers which also depends on h. So, basically we can write that this difference is plus some error, which means I can calculate, if you give me x, if I know the function value at x, then f of x plus h can be calculated as f x for very small h, it will be almost similar to, you should write f of x plus h plus error. Now, what is happening when h is becoming smaller and smaller, these two limits are becoming smaller and smaller, the interval minus that this interval around 0. this interval is shrinking down. So, that is exactly the issue here. So, when the error becomes smaller and smaller, that is mod of h becomes smaller and smaller, x plus h is very near x, then f of x plus can be safely approximated by f x plus f dash x h. So, basically function value at a given point can be approximated by the value of the y coordinate of the tangent at that point, at the point x plus h and x plus h f of x plus h. So, this is something very important. This is the key idea about the derivative. This is what the derivative does. It allows me to do a first order approximation. This is called a first order approximation, where you have at a given point. So, if you know any point function value here, then any point here, nearby point here, the function value can be computed by computing the y on the tangent, because the difference is error is very small. The more you come towards x, the error goes, the approximations become better and better, and in the limit they are the same, you get back the function value. So, this is something very important and it has to be kept in mind. Most of the cases you evaluate your limit, your functional values. When you are starting to learn derivative, you evaluate your first expressions of derivatives of a given function using this limit, by calculating this limit, which is called the approach through the first principle. One of the most important classes of limits that we work through is the following. One of the things I want you to think about is the first a fact which I have not mentioned, but I will just state, but I want you to try out its proof at home. It will be interesting exercise. So, if f from R to R is differentiable, so it is not just differentiable at one point of x, the definition here was differentiability at a given point x, but here when I say if it is a differentiable function, means it is differentiable at every point x in R. If f is differentiable, then f is continuous. F is continuous or not. So, this is something which you can try to prove yourself. Actually, use the definition of the derivative. It is good to have some exercise done like this, so you can be doing something interesting. Okay. Now, the second point is how to calculate. For example, one of the most simplest functions that you are asked to find the derivative is x to the power n. So, here when you find the derivative, the people immediately, without blindly thinking, would use the formula. So, how do you calculate this from the first principle, and what should be the value of n for which this is valid? Now, it is very important to understand, suppose I take n equal to 2 or n equal to 3. So, by your definition f dash x is, so x to the x is 3 x square. Okay. Now, suppose you might say, okay, then it is fine, you can just calculate, and but when you look at this formula, right, and when you put x equal to 0, then what you will have? F dash of 0 is n 0 to the power n minus 1, right. So, if n is not bigger than 1, then you will be in trouble with at this point. If n is bigger than 1, then of course you can write 0, say suppose it is 3, then it is 3 minus 1 2, so 0 square is 0. But if n is half, so what will happen? If n is half, it will become 0 to the power minus half, means 1 n by 0, 1 by 0, 0 to the power half, and immediately you have nothing. You are dividing by 0. So you have to be very cautious about this n. So all your formulas work good. So whenever x is, for example, let me just try it out. For example, if I have f of x, I am calculating for this function f dash at 0 for this x to the power n, then I will have 0 plus h to the power n minus, because here if I put 0 and n is see if n is not greater than 1, so you have it like this. So basically you have the limit as h tends to 0. So here you will immediately have this is nothing but limit, h is not 0, and that will give you 0 if n is bigger than 1. If n is not bigger than 1, then you will have a problem with this definition. So suppose n is equal to 1, obviously if n is minus 2, 1 by x to the power 2 x is not defined at 0. So you can say, how do I calculate the derivative there? Fine. But x is minus 1, then 1 by x, it is not defined at 0. Now suppose x is equal to 1, so fx is equal to x, right. Then if you put, so here it will become 1 minus 1 0. So if you put any x non-zero, so if n is equal to 1, then if you put f dash x and x is non-zero, then it will become n x to the power 0 and n is 1, so it will become nothing but 1. Or what about 0? You just cannot put 0 in here. You cannot put 0 in here because then 0 to the power 0 is undefined. So for the case when fx equal to x comes, you really have to compute the derivative from the first principle at 0. So in that case, you will have f dash 0, 0 plus h minus 0 by h limit h tends to 0, which is h by h is 1. So its limit h tends to 0 or 1 is 1. So you cannot just put that 0 into this formula and so the answer is 1. So there are certain points where you have to be very careful even with such basic functions. Your logic has to be absolutely clear. Now we will provide an example of a function which does not have a derivative but yet a continuous function. Please try this at home, please. This is a very good exercise. So if you do this exercise, you would have understanding of the structure of the how do we write this, how we have played with these things here with this epsilon delta structure, and you will have a very clear idea. Actually, the expression that we wrote here is very much required to prove this fact. Now, this is a standard function which is studied everywhere, fx is equal to mod of x, and this mod of x is not differentiable at 0 because so you take the right limit, which I write like this, h tends to 0 plus, so it is called the right derivative. So f of, so mod of 0 plus h minus h by h. So if h is positive, mod of, sorry, this is 0, mod of h is h, so it is h by h is 1 and hence the limit would be 1. But if I take this as a symbol of the left limit, then so this is mod if h, since h is negative, now is going to 0 from the negative side. So, then this will become minus h by h. So, the limit of this as h tends to 0. So, this is nothing but minus 1. So, the left limit and right limit are not the same as f approaches h approaches 0 for these functions, but hence. But if for example, if you take mod x cube, this has a limit at 0 and that is 0. Or mod x to the power 5, mod x to the power 4, does not matter, the limit exists and is 0. Only in this case the limit does not exist. But remember, this function is continuous, this is a very standard absolute value function. Absolute value function is what? It measures the distance from 0 of any point. When you are at 0, the distance from 0 is 0. As you move away from 0, the distance keeps on increasing, and that is exactly what the function represents. The distance of a point on the number line from the origin, right. Now, there was some very typical type of function things we had studied. Does every continuous function need have a derivative? This is an example. Another example is the following, where the function was discontinuous, but we have used the technique of removable discontinuity and obtained a continuous function. For example, if I have f x equal to x sine 1 by x when x is not equal to 0 and is equal to 0 when x is equal to 0. Now, this is a continuous function at this moment, you know how the function behaves. I have already drawn pictures of this, but the funny part is that this function is not differentiable at x equal to 0. When x is not equal to 0, you can easily calculate the derivative for those who know how to calculate derivatives. But if you, even from the first principle, if you do not have, but if you come to 0, then there is a problem. Then again, if you go by the first principle, then let me write down. So, I have to find this limit 0 plus h, 0 h sine 1 by h at a functional value at 0 is 0 divided by h, and h cancels because h is actually not equal to 0, limit of h tends to 0 sine 1 by h, because as h is tending to 0, say it is tending to 0 from the right side, it does not matter. What would happen? It is tending to 0 from the right side means sine 1 by h becomes bigger and bigger and bigger. But as it goes bigger and bigger, if you look at, remember the graph of the sine function, its sine values oscillate between 0 and 1, it does not stabilize to any limit. Similarly, if you take the other side, if h is negative, right, if h is sine of say minus h basically with h positive number, then what would happen? This value would become smaller and smaller on the negative side, but bigger and bigger on the negative side means smaller and smaller, but the sine function will continue to remain oscillate between 0 and 1. So, you cannot even compute a right limit, the right limit does not exist nor the left limit exists. So, the limit, this limit does not exist. So, here is an example of function continuous again, which is slightly where we have made it continuous artificially by using this technique of removable discontinuity, and the derivative is not existing. However, if you change the function a bit, you see why you put x square. Squaring is always some sort of a smoothingness. It's a regularization sort of thing. X not equal to 0 and is 0 when x equal to 0. Now what is f dash z? 0. F dash 0 is nothing but limit h tends to 0 h square sine 1 by h minus 0 by h. So here h which will cancel will become limit h sine 1 by h as h tends to 0. Now sine 1 by h is bounded function. So sine 1 by h is a bounded function. It cannot take any value without outside minus 1 plus 1. So it always remain within that bound minus 1 plus 1. So I can, so because of that, as h tends to 0, this limit, this value would go to 0. So this value, please remember, sine 1 by h is a bounded function. So basically if you have two functions f and g and if one of them is bounded, right, then the other one and the other goes to 0, then the whole product of those two will go to 0. So this is some simple idea. This idea is that you see as h becomes smaller and smaller, this value keeps on oscillating between, you might say, okay, what about this, oh, these values are oscillating, so I do not know, maybe this whole thing is oscillating. But no, as h becomes smaller and smaller and smaller and smaller, it does not matter what values they are taking, the values would ultimately, it will become so small, and because this value is only between minus 1 and plus 1, this value, the product value will start becoming smaller and smaller and smaller. So because here I have a fixed range, so suppose I am taking any number between 1 and minus 1, but my value becomes so near 0, say from the positive side only, let us check that, it becomes so near 0. So it does not matter whatever be the value I take, the value will finally become smaller and smaller and smaller. So another way of looking at it is, if you want to find this limit, right. So basically I have to show that given whenever mod h is less than this, so what is this? So this can be, this is less than mod h into sine of mod h. So this is less than mod h. So whenever mod h is less than delta, so if I choose my epsilon delta to be equal, then this is less than epsilon delta, and my delta is my, if I chose my epsilon, if delta to be equal to my epsilon, then this will immediately show me that h sin h has the limit 0. So you can do it in either way, you can have this conceptual thinking that what can happen even if the numbers oscillating, if I keep and if I am forcing another thing on it which is pushing it to 0, then what would happen. But you can straight come out from this rigorous way of looking at it. But I would be more curious for you to know that once, but of course you can compute the derivative of this. The question is the derivative continuous at 0? That is the question, and can you answer that? So think about this. We have still many more things to talk about the derivative. We will talk about its nature, its how do you differentiate. Of course there are higher derivatives, so you can have a function f, you can take its first derivative and then you can again differentiate the derivative. Derivative is a function of x, you can differentiate it. Again you can differentiate the second derivative. So you can keep on doing it. So something is called the nth derivative, f n x. So you have differentiated it n times, if it is possible to differentiate actually. So for example, if you have ddx of f x and you want to again differentiate it, you get the second derivative of this. So that is written as, so similarly you can get the third derivative and fourth derivative, fifth derivative, nth derivative. So once you know about the derivative, the rest of is just an extension which we do not want to discuss, which is very simple. Maybe you would have some problems. Okay, so with this we have this basic idea of the derivative, especially the initial approximation, which is important, and knowing fully well that all continuous functions need not have a derivative, and also looking at the nature of this very special type of very pathological functions. So, we have generated some idea of doing the derivative. Of course, I am not going to give you examples which are there given in standard high school classes of finding from first principles, but here for example, I am trying to show you that even when you are looking for very simple things, you should be very, very careful. So, this is done once this is the basic idea of the derivative is in place, specifically when I have written in terms of epsilon L delta. So, the whole idea is that the derivative is a first order approximation. It tells you that if you move a very little from the point x, then the functional value of f of x plus h is nothing but f x plus f dash x h plus some very small error, which for many practical purposes you can ignore. Physicists will simply ignore that error, and they will take f x plus f dash x h as something which is practically applicable. Okay. Thank you and see you in our next lecture.